All right, welcome to today's video. Today we're going to be talking about the stack. So you'll see here with the diagram similar to ones we've covered in the past, and that we have with our main memory. When our program runs, we have an address space that's allocated to virtual memory that's allocated to that program. We have higher addresses and then lower addresses, and these sections that we've talked about in between. And so the stack lives, generally speaking, in this location. What's important to note here as we're looking at this diagram is the direction that this arrow is indicating the direction that the stack grows, and the stack is going to grow from a higher address to a lower address, and from a lower address it's going to shrink back to a higher address. And that's really important to understand when we start looking at the actual instructions and how we keep track of where our top of our stack is, and then how we can get values, arguments, and local variables and other things out of the stack space. So this is generally what's happening, and probably the most important part of this diagram here is in looking at the higher and the lower addresses. Okay, we've talked a little bit about virtual memory here throughout the semester. Every process that runs has its own unique address space, and the process sees that as a contiguous block of memory. And so if we look at a diagram like this, we have a contiguous block of addresses starting from our highest address to our lowest address, and depending on whether you're 32-bit or 64-bit will determine the total number of addresses that you have. The virtual memory, the maximum address is the maximum value of a 32-bit pointer, although you don't have all of the addresses available. Under the hood though, the operating system, when we start dealing with physical RAM and where is this memory address actually pointing to, it's not necessarily contiguous. You can have fragmentation. You can have the memory scattered about through in RAM, primary memory. You can have paging, and that you might have certain portions of that application's memory actually written to a disk, and it needs to be loaded. And so, but for us, for the program's sake, the virtual memory is contiguous, and how we will treat that as we're writing our programs, our assembly programs, is a contiguous space. Okay, here's the layout again, and I guess I just fell in love with this diagram because I put it in here a couple times, and we don't have anything I necessarily need to point out each time we see it. Okay, so what specifically is the stack? Well, the stack is a region of memory, and it's pointed to by ESP being our extended stack pointer. So now we're finally getting to the point in the semester where we're starting to focus on other registers, right? We've had all the registers that we've been looking at. Most of it we've been focusing on the general purpose: ECX, EBX, EDX, and EAX. The stack, we push and pop. So we push things on and we pop things off of the stack, and so that gives us a last in, first out type of an operation. Depending on how you've been introduced to the stack or studied it on your own, generally we start with an introduction to a stack like this model. And that as we push values on to our stack, right, we stack them down here. So if I push 1, and then let's say I push a value of 2, and then I push a value of 3, 3 is on the top of my stack. It was the last thing that I pushed in. So when I pop things off, 3 will be the first thing that comes off. And so in order to get to that first thing I pushed on, I have to pop everything subsequently, and so it grows. Now, what I'll probably change up here a little bit is the direction in which I refer to the stack. And so if you go back to our diagram here, you can see that we have higher and lower, and that our stack is growing from higher to lower. And so what I like to do is I generally like to draw my stack in a way that represents this diagram more. And so as the stack is pushed things on, it's going to grow in this direction, right? We're going to grow towards lower memory addresses. As we pop things off, it's going to grow to higher memory addresses, or shrink to higher memory addresses, depending on how you want to look at that. But this is how I typically draw them or diagram them. So kind of the opposite of what you previously saw. This right here being the top of the stack, and then this right here being the base of the stack. Okay, so what will we use it for? Well, for 314, we'll primarily use it for function calls. We have the ability to invoke a function There's some information that we're going to save. We're going to talk about that, not just today, but through the next couple of lectures. We'll be able to pass parameters, store parameters for a function call. We'll be able to store information, like the return address, for when that function is done and it needs to return, so that execution of the program knows where to go to. Once we're in a function, we're going to use it to store and allocate space for local variables. That's why that's why when a function is done, local variables go out of scope and they're destroyed. It allows for context to be saved. So if you're about to call a function from within another function, then we have some commands, and we'll talk about those here this lecture, that can save the state of the registers so that that function can call, utilize the stack in any of the registers, and then return and restore the state. The stack will get overwritten, and so as this stack expands and contracts, as we use it, write values to it temporarily, and then deallocate or free up that memory, it will get overwritten. And so we don't typically think about using the stack for long-term storage of values or data. We'll be thinking about putting those in the heap or the BSS, and we'll talk about that a little bit later. Okay, so as far as our operations, we have a handful of operations or instructions that we need to talk about. The first ones, the primary ones, are how do we get values onto and off of the stack? Well, we have push and pop. And keep in mind that our stack is going to grow from higher to lower, right? And that ESP is what points to the top of our stack. So every time we push something onto the stack, that means our stack gets bigger, we subtract 4 from ESP because we're growing to a lower memory address. What we're pushing then is the data from the location pointed at by whatever. I'm sorry. What we're pushing is whatever value is here at X. We could push an immediate, we could push a memory location, we could push a register. I could say push EAX. That'll push whatever value is in that location onto the stack. It'll push it to wherever ESP is pointing to. Because remember, ESP pointing to the top of our stack, ESP is just pointing to a memory address. It's pointing to that place in the virtual memory where we can start to store data. We can pop X, pop a value, and what that does then is it increments ESP, and then it stores whatever was on the top of the stack at that time in the given location. All right. One thing that we'll need to make sure that you do is to coordinate your pushes and your pops. It's very important to do that. So if you push, that means you have adjusted the stack pointer. Then you need to pop. You need to restore that stack pointer to where it was before you modified it. And we'll go through. In the next couple of videos here, we'll go through into much more detail exactly why that is so important. And we'll probably even talk about like a real simplistic buffer overflow as well. Okay, so let's look at some examples here. Let's look at a little bit of code. Okay, so inside this program, I'm going to do a couple of things here that we'll circle back around when we start talking more about EBP. First thing that I'm going to do is we're just simply going to dump the registers and see what we have for a value here. All right, so we have EBP and we have ESP, and you can see that both of these are pointing to a memory address, FFCA6C44, and they're both the same thing. And that makes sense because what I did right here was I pushed EBP, so I took whatever the value was in EBP and I moved it to the top of the stack, and then I set the current value of ESP, so the current location of the top of our stack, I moved that into EBP. So that's why we're seeing both of those values being the same. Okay, let's say I don't even need to use a register here. Let's just say that I want to push a value onto the stack. So let's just push 20 hex. Okay, we have a new function here that will help us. It's very useful, and that's called dump stack. And the way that dump stack works is this is our label. So just like we've been using dump regs, and we've just been passing a value so that it can print off here in our output in our terminal just to help us keep track of the dump that we were dealing with. We have the dump stack, and I've actually got a reference here a little bit later on in the slide deck. Right, here's a useful library function. So the second argument then is the D words below EBP, and the third argument is D words above EBP. So again, when we start talking about EBP, this will make more sense. How we can use it right now, though, is that we can just leave it at 0, because we're not worried too much about what's above EBP. We are interested in what's below EBP, because what's happening is this is our base pointer. We're moving ESP, and so this is just allowing us to look at the contents of the stack. So we pushed one thing on, right? We push in 4 bytes. We push in D words, and so we pushed on a D words value. This gives us essentially will show us the contents to the top of the stack, right? So we push one thing on. We want to look beyond EBP 1 D word. So if I save that and run the program, we'll see here is the top of our stack right here. Right? How can we confirm that? Well, if we do a dump registers, then what we should see is where does ESP point? FFBB4040. This is the top of our stack, FFBB4040. And then you can see the value of 20, which is what we pushed on. Our stack grows to lower addresses, and we can see that this is the address. FFBB4044 is a higher address, so we know that this is in fact the top of our stack. This value actually comes from this push EBP, right? And again, we'll talk about that when we talk about EBP a little bit later. All right, so we coordinate this. So let's say now that I want to push 30 hex. Okay, now I want to look at 2 values on top of the stack, and I would need to have an additional pop, right? For every push, we need at least a pop. All right, so there we go. There's 20 and there's 30. 30 is the top of our stack. 20 was the first value that we pushed on. We can look at ESP, 39 DC, and that matches up with that address, right? So we can see that. And we could just continue, right? Every time that we push, we could push another value on. We'll just have to adjust how much of the stack that we want to dump, and then we'd also need to do another pop. Right, and there we go. Okay, it's not always apparent that if you don't coordinate your pushes and pops, that you'll get a problem with your program. Right, you can see here that I didn't coordinate that. I did pushes, but I didn't do pops, and nothing happened. Nothing happened in this case. But oftentimes you will find typically a segmentation fault. You'll find an error in your program. So make sure that you're being diligent in maintaining the coordination between your pushes and your pops. Now, another thing that you can do, let's just talk about this right now, is that you can also directly increment and decrement ESP. So we can do subtract and add to ESP instead of doing pushes and pops necessarily. Right? So if we did sub ESPX, then we would subtract whatever that number of bytes is from ESP. Oftentimes you'll see that when a function is called, that this is done, and we'll talk about that here in the future. We can also add to ESP, and so if we subtract from ESP, we're moving ESP, we're growing it to a lower address, so we're freeing up more space on the stack, which is typically what you see. We're going to free up space for local variables. If we add to ESP, we're making it move back to those higher addresses, back to the base, and so that's deallocating that space on the stack, or making it available for for later usage. And oftentimes you'll see that when you leave a function. So if we allocate space in a function for local variables, once we're done, we'll need to move ESP back to its original location because we're done with that space. So in this example, what we could have done is if we push in D words, if we push in 4 bytes, then instead of popping 3 times, we simply could have added to ESP 0C hex. And we'll see that when we run this program, it still works, although it worked before. But we'll add in some additional instructions here, and that would cause an error. All right. And ESP, and sometimes you'll see this. You won't have to do it directly in any of our programs here, but certainly if you move on to the reverse engineering course, you might see something like this. And what this is doing is it's ANDing ESP, making sure that ESP is on an even byte boundary. And if you're interested about that, we'll get into more detail in 444 about data structure alignment, and that making sure that those addresses are on some sort of a 4 byte or 8 byte or 16 byte boundary or whatever. So it's something you can look into, but every once in a while you'll see that instruction. All right, next thing that we'll take a look at then is the push A pop A. And what this operation does, so sometimes you see just push A, sometimes you see push AD. I'll use push AD for 32-bit operations. What this does is it essentially saves all of the registers here, pushes them onto the stack. And then pop A pops them off the stack in the reverse order. So it essentially restores those. And so you'll see we push EAX, ECX, EDX, EBX, the original ESP, EBP, ESI, and EDI. And so what that means by original is the value of ESP before all these pushes occur, not the value of ESP as we're pushing these values on, because we're modifying the stack pointer as we're pushing. So that's why it says the original ESP. Here you can see an example. So I'm just going to move a bunch of data into those registers just so that it's apparent what we're doing. We'll dump the stack, and then we'll do a push AD, and then we'll dump the stack again. So let's take a look at the results here. And before I do that, I'm going to go back and just comment out some of these dump regs, just because we're going to start generating a lot of output here. All right, so this is, again, this is the bottom of this output is the top of the stack. Bottom of the output is the top of the stack. And this is before I do the push AD, and this is after we do push AD. Before, there's a bunch of stuff there, but it's just data, it's garbage, it's junk inside of that memory address from previous operations. After I do a push AD, you can see the last thing that we pushed on was EDI, and the value in EDI is 8. So we have 87321, and then EBP ESP. So the original ESP, which would be this value, and then EBP. Okay, and so you can see those values line up, and that is the condition of our stack right now. This is original ESP, and this is the original EBP, and you can see that they're the same values. And that makes sense, because if we go back and look through this code, right here, one of the first things that I did was I moved ESP into EBP. All right, I modified the stack, pushed 3 times, and then added ESP, 12 hex or C hex to ESP. But even though I modified it, when this code executed, the effect on ESP was the same. Right? It started, we pushed it 3 times, and then I adjusted it back to where it originally started. So by the time we get to this instruction, push AD, EBP and ESP are equal values again, right? Because they're pointing to the same location, because that's what this instruction provided for us. All right. Let's go ahead and make another modification to this program. So after the push AD, I'll modify EAX. And we'll go ahead and we'll do a dump regs, and I'll call this 2. Won't have to worry about the dump stack content right now. Okay, and then we'll do a pop AD, and we'll call that 3. Okay, so EAX had a value of 1, and then we do a push AD, so push all those values onto the stack. Then I move into EAX a value of 9 and do a dump registers. So we can see number 2, EAX does have a value of 9. After that, pop AD, so we restore all that content from the stack back to the appropriate registers and do a dump regs 3. And what do we get? Well, we get a restored value of 1, as well as, if you look at all the registers, all those original values that were there. Right, so that's how it works. Pushing it on, pushing all those register values on, and then popping those off. I do want to go back and talk a little bit about calling a function. And what happens in just kind of this introductory level is we call a function. The function name is a label. And so when we call a function, what we're doing is we're really telling the instruction pointer. So remember that we have EIP as our instruction pointer, and it controls the flow, the execution flow of the program. And so a function name is really just a label that points to a memory address. And so when we call a function, what we're actually doing is we're pushing the next instruction onto the stack, and then we move EIP to the location of where that function is. So execution jumps to that function, something that you start learning early on when you start programming. The fact though that we push the address, we're pushing the address of the next instruction onto the stack. And this is pretty important because once our function is done executing, this is how it knows where to return. When our function returns, this is what allows that to happen. And so in our functions, when we return from a function, one of the last things that we do inside of that function is that we pop the return address off of the stack, and then we move that address into our instruction pointer, which is what allows execution to return. So I'm just going to scroll down here a little bit to the bottom so I've got a little bit of room. I'll create a very contrived program here, and let's say that these values are our addresses. So I have an instruction at 0, at 4, at C, or 8, and at C. And the instruction here is simple, push 1, and then let's say that I have a call to function, and then because I pushed after the function call, we're going to have to make sure that we clean the stack up or adjust our stack pointer. So I'll add to ESP 4 because we only pushed one D word, 4 bytes. So we'll add 4. And then there's nothing here to concern ourselves about. Okay, so what happens with our stack? Well, right now we have ESP and it's pointing to the top of our stack. So let's just say that as far as we're concerned, nothing's there. EIP, on the other hand, is pointing to 0. Right? So let's say that we're right now the value of EIP is the address 0. Okay, so execute that instruction, push 1. So we push 1 onto the stack, and our stack pointer, I meant to draw that like up there. So now our stack pointer is pointing at this location. This is now the top of our stack. The top of our stack has a value of 1. We call our function. So before execution goes to whatever address, wherever function's at, let's say that later on in our program we have an address of 20 hex, and that's our function. Before it does, it's going to push the next address on. So in this case, it'll push a return address, and that address is 8. And I'll just put return and address of 8. Okay, I guess I can't do little dots. Right, now our stack pointer will adjust. This is the top of our stack. And now EIP will no longer point to 0. It'll now point to the address for our function. So in this case, it would be 20 hex. Right, the function does stuff, and more of those details to follow. When the function's done though, and it goes to return, it pops this value. So by the time that we're done and we're ready to return from our function, we'll ensure that ESP is pointing here, and then we'll return. We'll pop that value into EIP. Right, so we'll pop that value into EIP, that address, and that will decrement ESP. So now ESP will be pointing back to this location, right, back to our 1. So if we move that address into EIP, that was the next instruction. Right, so we went from here, we executed the call, now we return to here, and we still have this value on top of our stack, this 1. And so now we add 4 to ESP, and that takes our stack pointer and it points it back up here where we originally started. And so that's the general flow. Without getting into the details of what happens inside of that function, that's the general flow of our function call. Okay, we talked about dump stack. We saw a couple of examples there. And the last thing that we'll take a look at is Printf again. And we've already talked about Printf. We've already used Printf a little bit. But now that we're specifically talking about the stack, we can get into a little bit more detail with that. So we'll just do a Printf example. I have a format specifier here, Printf, %d, %d, %d. So we know just by looking at that. Printf is one of those functions that's relatively unique in that it takes a variable number of arguments. We determine the number of arguments we pass to Printf based off of our first argument, which is %d, 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 the format specifier. So this will, when we call invoke Printf with this format specifier, we'll need a total of 4 arguments. Printf is an external library function, so we need to define that, extern Printf. And now we can go down and we can call. So here is that function. Right? This is equivalent, this is basically what we're trying to do. You'll notice though that the way that we have to push these values on is the first argument is the last thing that we push. the last argument is the first thing that we push. So if I want to print 1, 2, 3, then what I need to do is I need to push 3, then push 2, then push 1, then push the format specifier, right? Because this argument is an address to a string, char pointer, right? And that's what format gives us. Then call printf, and then make sure that we clean up the stack when we're done. We had 4 pushes, so 48C10 hex, that's the number of bytes that we need to adjust. Okay, so we make those changes, and now when we run this program, we can see printf 1, 2, 3. Okay, if we got that wrong, let's say that we did that in the reverse order, the only thing that would have the most significant impact would be if, let's say that we pushed format first and then we pushed the integer values. See, we got a segmentation fault, right? Because what it expects for the first argument is an address to a pointer. We pushed a value of 1, so it tried to access that as a memory address, and that's not a valid address. So that's where we get that segmentation fault. All right, let's see. So there's some references there. All right, so this is an introduction to using the stack. So what you're going to be looking at understanding right now is really how does the stack grow from higher to lower? How are we using these basic commands? How are you pushing, popping, pushing, adding in order to make sure that you're coordinating your stack movements, understanding that ESP points to the top of our stack. And something that I didn't do here, and we should actually go back and just take a look at real quick before we wrap up, is if I dump the registers as we go, with every single push movement, or push instruction, sorry. So I'll add those in. And let me comment these out just to clear some of the clutter. Right, what happens to ESP? Well, we can see that the value changes, that it decrements with each push because it's growing to a lower address. C50, C4C, C48. We're done. So we add ESP, we add those same bytes to ESP. And now when we dump the registers again, we'll see that ESP is back to where it started, which in order to confirm that, we'd need to do a dump regs before any of those pushes. Right, so here's ESP originally, and here's ESP once we're done. Right, it's important that we restore that value. So these are all the pushes, and then we did an add, which gets us back to our original value. Right, so that's really the important thing right now is being able to understand what's going on with the stack. The next component to this then is introducing function calls, being able to pass arguments to a function, exactly what happens to the stack as that occurs. How do we access those arguments? Because you'll notice as we're pushing values on here, we're pushing them and then we're calling the function. And so we need to be able to access those variables inside of the function, those values inside of the function. We'll talk about the stack pointer, or the base pointer, EBP as well, and the importance of that. And then we'll probably talk a little bit about just some basic security concerns and buffer overflow type stuff. Relatively old, been around for a long time, but it's worth going through, I think, at this point. So let me know if you have any questions on anything that we covered. The code will be updated and are uploaded to our course material, as well as this annotated PDF. So with that, that's all I have, and I'll talk to you guys in our next video. Thanks.